Yeah, let's so. Ew. It's on the calendar. Yeah. Does bro know? Oh yeah. You said it. I don't know if I can do this. No, I'm just you know. You can tell this. You can tell her that. What? Oh my God! Oh, they're all side. Yeah. I don't like this. They used to have so much fun helping people you didn't even know it yet. We were like, oh yeah, we used to feel it, yeah, we used to raise it out. It's like, okay, yeah, that's good. We were like, you're seeing that. And he goes, well, I know about so, yeah, so James thinks we're done. We're done with my It's just like a, it's a picture always.
All right, let's get this class started. How is everyone doing so far on the project proposal? Everyone all turning? And not yet? Okay. How many of you have met with us already? 50%, hopefully more than 50%? Okay, perfect. All right, cool. And you think I'll get useful feedback? Do you have, I'll have ideas what to proceed from this point. All right, cool. So today we're going to continue our lecture around the analog signals, and this lecture specifically we're going to talk about something that we kind of briefly bring up in the previous lectures multiple times. It's the ADCs, or analog to digital converters. Before the class content, a few of the announcements we want to have. The homework 6 is going to be due tomorrow at the midnight. As usual, we have 1 day of the late submission for like 10% off the grade, but try to submit on time and get the 4 points. And we will be having, like after you each have the project proposal review meeting with us, we're going to have the proposal resubmission or like the revision due on the Tuesday after the spring break, so the March 11th. Hope that will work for everyone's schedule. I know most of the teams we met with, it's mainly about adding more components or switching components so far. So hopefully that's okay of a workload. We do have a couple. We do have a few groups. They might need to try a few components. So if you are one of those groups, make sure you have the components to try out before you hit the spring break, so that you have some time to try it out and then finalize on which components or which use cases or applications you're trying to build for the final project. And the homework 7 is also released. That's going to be the last homework of this class, and it's due on the same time, the Tuesday, 11th of the March. And of course, our favorite midterm 2, the exams is going to be on the week after that spring break on Friday, as usual, in the same locations what we did last time. The seats assignment is going to hold the same for pretty much whichever room you sit in. We're going to ask you to stay in the same room. Any questions so far on these assignments? That you have the whole spring break. Take some time off, and then after you come back, I'm sure you'll have enough time to study the exam and everything. Yes?
Will the practice exams be released?
The practice exam will be released, I think this weekend, if that works. Or do you guys want it earlier? A week should be more than enough for the practice, hopefully. So it will be released during the spring break. We're trying to release it before next Monday, but it will be during Any other questions? Oh, again, we will have another review sessions, review lectures on the content during the week of the exam, either on Tuesday or Thursday. Depends on, what you guys feels like. But any other questions? Okay, perfect. So starting the week after the exam, we'll be starting the student presentation, or like kind of like a mini lectures within the class. Basically, we will be assign a topic to each of the groups after we finish all the team review sessions with you on the project proposal. And then based on the components you choose or like type of communication protocols you end up using, we have some commonly shared topics that we can randomly assign to the groups that have those components in their project, and for those groups have something like special in their component list or in their communication protocols. We will pretty much ask you to do like a mini lecture on that one. So don't get scared. You will have like a 30-minute slots before your presentation with the teaching team. We will go through the slides you prepared together and the content, so that you will know that what the material is prepared and everything. It's good for the time. We're thinking about 15 minutes per team, but that might vary based on how the first few lectures goes and how many times we have left in the class. Basically, each of the team members are required to attend at least that presentation sessions. We will release the sign-up sheet this is going to be after like spring break. These things will be posted on the Piazza, but just give you a heads up. These are the things you'll be expecting after the midterm too. Any questions regarding this student presentation, topics, group assignment, or anything? Okay, perfect. So yeah, as we mentioned various times before, communication or presentation skill is actually quite important. And in the end of the class, you will be presenting your final project to a certain extent. So this will be served as a practice/learning session for you and for your peer student members. We will be we will be grading each other on this student presentations. We're not gonna do like a ranking, so to speak. It's basically, everyone could have 4 points on this if you prepared accordingly. So hopefully that's, yeah. Any questions before we move on to the content of the day? Okay, perfect. So a little recap from the last lecture. We basically did an overview of the analog signals in the embedded systems. We talk about like how do we sampling the signals, and we touch on how we could do the data conversion from like an analog signal to a digital binary value. We also, showed you a little bit of research, but we didn't have enough time for that. So if today's lecture we have some extra time, I'm gonna show you those slides if we have enough time. But the main course of the lecture is gonna be the ADC, the analog to digital converters that we frequently brought up during the lecture so far. So just like before, there are a bunch of reading materials in case you are very curious of how they actually works underneath and want to get more information or implementation details around these topics. There are a few quite good resources, again, like the recommended textbook we have, the embedded system with ARM Cortex-M microcontroller, have a whole chapter around the ADC, and we have our old friend, the reference menu, that also have a section on the ADCs, just in case you want to know more hardware or like circuits related stuff. So today's lecture, today's outline around the ADC channels is, first we're gonna talk about the sample and hold circuit, which is like a critical components used in, I think, almost any ADC architectures or ADC structures that use to hold the values of a analog voltage value and then just hold that in a circuit for your microcontroller to sample and then turn that into a digital value. And then we'll also talk about different types of ADCs. 3 of them we're going to talk in a little bit more detail: the flash ADC, the single slope integration, and the STAR, the successive approximation register. So these are the most commonly used ones and likely the ones you will be encounter during labs, during the microcontroller we're using, and likely for future applications for a while. And then we're also going to briefly touch on the ADC channels we have on the STM chip we're using for the class. So what is a ADC, analog to digital converter? It's basically like, it's pretty much like your job is to make a mini oscilloscope to convert or like sample the analog signals and then sample them into like digital values, so to speak. Especially except the ones you're gonna make or like we're gonna make, it's a little bit crappier. It's usually like less bandwidth and less tolerant on the voltage arrows. But like even if you look at closely at this one, even of this type of oscilloscope, like a pretty decent one, it's like a 10-bit ADC channels. So in terms of the resolution, the ADC channels you have on the say STM are kind of comparable, and it's just that these things are able to go like a heck lot faster and also much better at the error tolerance. Which is the reason why sometimes if you search for the Amazon, you can get some quite cheap oscilloscopes. Those are because you pretty much have like a microcontrollers underneath that do the ADC sampling rather than the like a big professional circuitry inside. So first part of the, I guess the fundamental components of the ADC or any ADC channels is called sample and hold circuit. it basically captures a analog value at a specific instant and then holds that value at a steady level and wait for like a short period of time, and then let the ADC on the microcontroller or any ADC channels to convert that into a digital value without any distortion, basically. This is like a simplified version of a sample and hold circuit. Basically, for this one, we have like two op amps there. So basically, the first one, you have on the top left, you have like some analog input coming into this op amp, and then whenever that switch is closed, that value, that signal gets to charge the capacitor in the middle, and the switch can close for like a relatively short amount of time, and after that capacitor is being charged, basically that value is the same value as the analog input at that instant, and then the the switch will turn open again, and the voltage got hold there, and then on the analog output side on the right, which is the same value as the voltage being held there, and then the ADCs basically do a bunch of sampling and then turn that voltage value into a digital value. So yeah, basically this. So of course, in the real world, like the sample and hold circuit are much more complicated than this, and usually the time that takes to, or time it requires to do the holding is much less than what this circuit will require. And yeah, because we're trying to let go of the circuit and then have like an instant of value rather than have like value that's distorting or like changing over that time, which can affect the values being sampled on the ADC circuit later. But basically, the op amp here works as like a buffer or like a voltage follower. Basically, hold whatever the input there, hold it for a short amount of time for the channels to take sample off. Any questions regarding this simplified version of the sample and hold circuit? Basically, you don't have to understand all the electronics details on the circuitry details of this one, but just understand this is how that fundamental component is working. Hold the value for a short amount of time, and then let the chip or let the other part of the DC does the sampling, and then after that is done, release it. Any questions on this so far? Cool. Yeah. So for these circuits, usually on the right side, the amount of the voltage will be only be affected by some, say, like leakage current during in the capacitors. And if we're doing it like a very short amount of time, those varies can usually be ignored. And let me show you how one of these circuits could look like. So let's see, I have it open here. Okay, here we go. So on the left here is basically the signal input, and then on the right is our sample and hold circuit. So if I just close this, switch, you will see that value got continuously sampled. Obviously, this is a kind of like an ideal situation. What's actually going to happen is pretty much like, depends on what's the frequency I'm doing this, just a bunch of these happening, and then you will still see on the right. It's a little bit stepped, but it's pretty much, like a good replication of whatever analog signal is here. And how many steps is basically depends on how many bits was assigned to this ADC channel, hence the resolution. If you have 10 bits, then it's like about 1,000 steps, which is very decent if you only sampling like a sine wave, for example. Yeah. And then whenever it's opened, that voltage value got held in the circuit for the ADC channel to do its sampling if it takes longer to do. Any questions on the sample and hold circuit so far? Yeah.
Is sample and hold always buffer?
Is sampling and hold always buffer? Yeah, because the op amp here usually pretty much acts like a buffer. It's a voltage follower. Any other questions? Yeah. But that buffer value does not affect the the voltage, like the analog input signal on them. So. So that was obviously like a more ideal situation. In the real world, some amount of the charge up time are required. This is usually due to some of the like internal resistance in the components you are connected to, or that from the circuitry, for example. And it will take like a certain amount of time. So instead of like charging up the capacitor instantly, you'll end up having some kind of like RC circuit, like a simple RC circuit here, to do the so that in the end that's going to be something like the charging up curve is going to look like something like this. And I'm not sure how many of you are familiar with this equation here, but basically, I think this T underscore C or tau here is basically R times C, and then that's the amount of time it takes to charge up to about like 63%, and then one more of these time, it would charge up to like 80, I think 88 or something. So that was the constant that you can expect it to cover. Like that's the time constant you can use to approximate, how many percentage of the current is being charged up inside of this RC circuit. So as always, then we're gonna have some like trade-offs here. The trade-off here basically is the sampling time versus how accurate or how small the error can be. If you have longer time waiting for each of these, charging time, like longer time for each of the sample, so that the charging is actually charged more closer to whatever the actual input on voltage, you will have like a more accurate sampling. But then if you do that too slowly, then you can have a slower ADC speed, basically. And usually these things are software programmable. The chip will allow you to determine what's the sampling frequency or like the sampling rate you want with any of the input signals. So here's an interesting question. Oftentimes actually, it's allowed you to sample much faster than the ideal charge up time. Let's say if we say like 90% or 95% is the ideal charge time, that we can do like a good sampling of the current input voltage level without considering too much error. But in real life, actually the chip or people, when they do the implementation, sometimes they do the sampling much faster than this ideal time. Any guesses or any thoughts on why they allow these functions inside of the program or inside of the chip? They have these options there for you to purposefully go faster than the ideal charge up time of the component. Any guesses? Imagine you will be sampling at, say, like 65% or 60, somewhere here, rather than sample the whole value. Yeah.
The voltage of the chip is like low enough, so even if there's error is not less significant.
I see. So on this one, from like 0 to 1, it is 1 volt, but you can think it like a percentage, so to speak. So you're saying if the voltage is low enough that, say, 0.3 volt out of 1 volt range is not too much of a big deal? Is that?
So it's so like you're sampling it like for 10-bit ADC, like the arrow between each between like 1 bit of arrow is like really small, and then the sampling takes time. So when you finish the sample, like the end of sampling, it might have charged up to like 99%. So instead of waiting for.
I see. So normally when we do like a sample and hold circuit, after it's charged up that time, the circuit basically turns open. So so if you hold at say 65%, then that's the value that the sampling is going to be looking at through however long that sampling time is. But I think that's a good thinking. So some applications might just doesn't require as high accuracy, and the lower accuracy signal does the job. Yes.
Maybe if you consistently sample before it's fully charged, you can scale that value by the same amount to essentially not worry about the fact that it's not fully charged, if that makes sense. Like if every time we sample at 1, we know that every value is 60% of what it's supposed to be.
I see. Yeah. That's very interesting thought, actually. I think there might be some people implementing something like that out there. I think normally that will require additional hardware to do so that you would know, like an additional compare circuit, which we'll talk about later, like a fancier compare circuits to know exactly what's the amount of, in terms of percentage, this sampled versus the actual input. But yeah, I think that's something that can be done, actually. Another reason why they allow these is if you look at this curve, obviously there's no unit on the x-axis, so you could be, normally it should be in microseconds, right? But say if you have some huge resistors in the circuit, etc., then this time can be a very long amount of time, and that will cause all sorts of problem. So basically the chip gives you the option of preventing this from happening. You always have some safety net. If it's hitting too long, we just get the sample down and then move to the next execution or next operation. Cool. Next, we're going to talk about the ADC building blocks. So the sample and hold circuit is like an essential part of the ADC structure. That's right at the input of the ADC. And then once that input comes in, there's a few more of other building blocks that typically exist in most of the ADC channels. The first one is a comparator. It's an analog component. We don't have to know all the circuitry details inside of that. We can just remember it as that block. Basically what it does is it compares the two voltage level on each of the two pins on the positive and negative input. And if the positive is larger than the negative, then the output become high. If it's lower, then the output become low. It's a very simple or it's a very simple yet very fast compare circuitry that basically finish the job in exact 1 cycle or less. And then we also have a resistor divider. You guys should be more or less familiar with this. Basically, if we have different values of the resistor put inside of in serial, and then at the midpoint between them, that value of that voltage is going to be divided proportionally to the resistance value of these two resistors. And if we have the two values equal to each other, that will basically give the voltage output here to be half of whatever the voltage in is. And any questions on these two, essential but very simple components block? They might look very simple, but you can think of them. They give us essentially two abilities. First is to test the voltage, and the second is to manipulate the voltage. And these two components, when they combine together, we can build some pretty cool stuff together. Pretty important combinations inside of the ADC. For example, this is a very simple structure when two of these building blocks putting together. It's pretty much just the comparator, and then we have the reference value of the negative input on the comparator circuitry connected at the half of whatever the VCC and the ground is, and then we have the positive signal to be whatever the analog input at the moment. And this will give us a essentially cutoff at half of the voltage, and then give a high and low based on if the current oscillating signal is above 50% of its range, or is within below the 50% of the range. You can think of it as like a 1-bit ADC channel, so to speak. Any question on this? So the analog voltage goes in, it's got compared to that reference voltage. And in this case, that reference voltage is being set exactly at half of the input range. So if it's above the half of the input range, the output will be high. If it's below the output, the half of the voltage range, then it will be a low. So yeah, 0 and 1-bit ADC right here. And just watch out where you connect the negative and positive terminal. Usually we just put the in on the positive, although sometimes that can be lower than the negative reference voltage. But we're all good on this. Very, very simple yet works very well block. Okay, cool. Then we're ready for the next, like how a actual ADC channel works. This is one of the most fundamental and also basic ADC architectures. It's called flash ADC. So this is what it essentially looks like. It uses the resistor ladder to generate evenly spaced reference voltages. So if you look at the graphs here, we have the V in, which is what the system is running on, and then all the way to the ground here. And then between each of these ladders, it's the resistor that have exactly the same value. So in this case, we have seven resistors in between. So each of these values are basically the reference value, the entire input range divided by 7. Like that. And then all of them got connected to a comparator voltage to just determine at that level if it's currently higher than that reference level or is it lower than that reference level. And after that, we connected to a priority encoder to convert it into a digital, convert it into like binary values. So in this case, we have say 8 different possible values, and that got converted into like a 3-bit output on the binary output. And this is essentially a flash ADC version at a flash ADC channel with 3-bit resolution. Does this make sense so far? Basically, we divided the entire reference voltage into 8 different values, and then we compare the input of this analog input to each of these values, and then based on where it landed in, we output that to what's the current voltage. And as you can see, it's actually a very, very fast operation because everything of these are connected and then they got converted in one go. So with this ADC, hence the name flash ADC, we can get the sampling. Once you pass through the sample and whole circuit, that value, we can sample that within 1 clock cycle. So this is like heck fast, very fast. It's used usually in like very high speed applications. For example, the oscilloscope we mentioned before, that usually use this type of flash ADC to give a very fast, very high bandwidth. Sometimes they also use it for like RF communications or like audio processing because of its speed. Any questions on this so far? We'll also look through like a circuitry to just give you an idea of how it looks like. Let's see. Can stop this and go to the next one. Yeah, so it might be a little bit hard to, okay, it should be. Okay. Here we go. Basically, the input, ADC input comes in and it goes through these resistor ladder and then goes through a bunch of comparator circuit in parallel. And then each time it would basically sample whatever that input at the time is, and then get converted into a 3-bit value. So if, say, we had, okay, right there. So this value is going to be here. Okay, so this value is going to be an 7, and then 0 to 7, which corresponding to this input value's peak value here. So this is essentially how this flash ADC works. The input goes in and then goes to a parallel resistor, goes into this parallel structure and then goes pushed out in one cycle. So, okay, let's get back to okay. So obviously, the speed is the big thing here. It's super fast, as the name and the conversion time is basically just defined by how much time the comparator and priority encoders does it's usually within like 1 clock cycle. On this circuit, the main delay usually is from the main variant of this is first, of course, what's the clock cycle you're using, and also second, how long the sample and hold circuit takes to do how long does that charge up time takes. So this is very fast, of course, they comes with some limitations. It's limited by the number of resistors in this resistor ladder system. Basically, every one. Okay, let me just. It's every one more bit added to the AND output. Essentially, you need double the amount of ladders you're building, because you're doubling the steps that sampling is happening. So essentially, it's I guess simple to consider how to build such a circuitry, but when you actually manufacture it, it's quite complicated because for any n-bit resolution, the demand exceeds. You will need 2 times n minus 1 amount of comparator unit, and then you also need 2 times n to the n power of the resistors needed for this. And again, for this one, with all those hardware components put together inside of this ADC channel, the power consumption of this would be much higher than the other structures. So basically, we have super fast speed, but there we're treating trade-off between the power consumptions as well as the amount of hardware components that we need to put into this structure. But any questions on this overall, the flash ADC? Okay, perfect. So next, we're going to talk about another structure. It's called slope integrator. The slope integrator ADC is a type of ADC that converts the analog to digital value by measuring the time it takes for a capacitor to charge up or decharged, and then use that compared to an input voltage using a consistent current source. So basically, the idea of this structure is that we do not want to use too many hardwares for a ADC channel, and instead we're going to be using something that the microcontroller is really, really good at, which we mentioned before, is measuring how long it takes for anything to execute. We're going to using the time as the variable rather than using purely hardware to build a circuit. So basically, the idea here is we have a input signal coming in, and then we will have some form of charging up slope. For example, let's just say this is a linear slope, and then we will the microcontroller just basically measures how long it takes from 0 and to a fully charged or charged until the reference point, and then use that as the value, and then divided by how many clock cycles it has. So each of the clock cycle could potentially be one of the value steps of that input signal. Okay, I see a lot of confusing. So you can imagine, basically, we have the signal connected to a comparator circuit, and it's just constantly doing the comparing, and it's always going to be, well, it's not always, it's usually going to be lower than the reference value, right? And then at some point, it became larger or equals to that value, and you lock the time of that. And then it goes back to 0, and you do the count again. Then essentially we will have the amount of time it takes from charging from 0 to whatever the reference value is. And each of this clock cycle can be essentially 1 bit or 1 step of whatever the value you're sampling with. Does this, like the basic idea make sense? Just, depends on basically how long it takes, and then you divide the whole thing by the amount of circuits, like cycles it has, and each cycle is 1 step within that range. Okay, so how is it actually implemented, right? As we mentioned before, usually like a charging up time is a pretty exponential thing, or like log thing, depends on how you look at it. So how are we going to be able to get a linear, in this case, or at least within like a certain range, a linear increase of the voltage based on the amount of the linear amount of time to charge up these values. What it turns out is that, I'm not sure if you take out like 215, any of you guys take, okay. So basically, if you don't use like a voltage source, if you use a current source of a constant current value, then when you use that to charge a capacitor, then the slope is actually constant. You don't have to, dig too much details in how that happens. It's just accept it as a fact. And of course, in the real life, like in the big circuits we build, it's very hard to have these work for like a large range. But inside of the IC chip, this is actually much manageable to do. We can have like a, say, current, like a voltage controlled current source to keep the current to be constant, current source to be constant within like essentially this, the voltage input range, so that we can keep a consistent current source for that amount of range, and then within that range, we use that slope to measure what's the charge up time for a given capacitor. And then we basically time it every time, and then we use how many amount of cycles within that to determine how many steps of the, or at any given time, what's the current input of the ADC channel. Any questions on this so far? We have okay, it might be a little bit abstract, but are you sure you don't have any questions? Okay, so let's look at, again, a quick, it would be a little bit more, okay, again, don't have to worry about on the left side how the circuit works, but let's just look at the right side. So essentially, we have the input coming in, and then it's just doing the counting here on what's the time it actually hits the reference voltage, and whenever that happens, it registers that time, and then you use that as the reference for the future things are coming. Like when you're trying to read a signal, this is essentially what. Depends on which cycle it has. It's currently at. This is the amount of the voltage it's on, based on like a linear interpolation. And if you want to have like higher resolution, essentially you will be using like a faster clock, which is, I guess. So this is the same amount of input signal, input voltage range, but then we end up with like a much bigger step counting result. For example, this one is like 65. So essentially, you have like a higher resolution of your sampling resolution of your analog input at a given sampled value from the sample and hold register. Okay, cool. I hope this makes sense. And then. And we have something like slightly fancier. So instead of doing like a single slope sampling, we also have what they call like dual slope integration. Basically, it not only measure the time to charge up, it does also measure the times for it to decharge. It's more complicated than the previous in the previous setup, the single slope one. And you can imagine the sampling rate for this will be slower, usually at least like double the time, because the amount of time measures for the decharging. But this is essentially a slightly more complicated design. You don't have to know exactly how they got set it up, but basically it gives you a higher accuracy in terms of it's more robust to the noise rather than the previous one. If we only measure one side, then if there's some like jittering in the signals, those could end up being, messing up with your measuring or messing up with your sampling. But if you're measuring both the increase, like the charge up time, but also the decharging time, you are like much more robust to the input noises, etc. Yeah, again, another like a quick summary of the slope integrator ADCs. Usually it's slower because it uses time to measure the current ramp, and that's pretty much however amount of clock cycles you want to devote it into that one sampling is how long it's going to take. Compared to the flash ADC, it takes exact one cycle to do the entire measure. Here it's take, however amount of cycles it needed for that input voltage to reach your reference. The resolution is very high. It's pretty high resolution. Of course, you can adjust that, but clock is something relatively cheap to play around, and also you have much more controls over it. So if you want to, you have the ability to have like high resolutions with this type of ADC. But usually it's better to use it for like slower signals because the speed thing we mentioned, it's usually sampled at like a slower rate. And complexity, it's kind of like a medium-ish. It does require some analog stuff, but mostly it's just the timers and comparing the timers inside of your microcontroller. So it's like kind of like medium complexity. The power consumption is pretty low. It's good for battery because a very minimal amount of hardware is used. So that's why the power consumption in the end can be kept low. And it's good for like battery powered multimeter, like those portable ones you use. Actually, most of the multimeter, like slightly better ones, they use the dual slope integrator rather than the single slope. But we would just characterize them into one category. Any questions regarding this? Okay, cool. And the next one we're going to talk about is SAR, or SAR ADC. It's a successive approximation register ADC. It's one of the most commonly used ADC converters in microcontrollers and embedded systems. And yeah, spoiler alert, this is also the type of ADC that's being used on our board for the class, the STM ones. So this is a simplified structure of this type of the STAR ADC. Basically, it's doing like a analog binary search for the value at some reference value. If you look close, we put like a DAC here. We will learn about this more in next lecture, but we kind of briefly talk about how we could convert a digital value to a voltage. We will talk more in detail, but essentially what happened here is it uses a binary search to basically you have like an input here, and then the comparator will be, okay, let me explain this as an example. So basically, the analog input goes in, and then the sample and hold circuit holds that value to the and hold that value and kept it steady. And then the STAR register, it's going to be, which is here, the register here, it's going to be start looking at the highest bit. So it would look, given giving the resolution we are having, for example, this is like 8-bit. The first, it will be looking at the 50% of that 8-bit, and then put that value inside of these DAC to convert it into a analog voltage, and then goes to this one compare. And if it's higher than that, it would. If the input voltage is higher than that, it will go to the second bit. It will keep that one as 1, and then go to the second bit, and then do the comparison again. So it's kind of like a binary search, if you think about it. And then after a few iterations, it ends up being with whatever the value is. If, for example, this one, it turns out the input value is like actually smaller than the 50% of the reference voltage. So it goes to the second bit and then gets essentially 25% of the voltage to the DAC and then use that to compare. So, and then gradually get like approximate number of the voltage. Basically, yeah, bit by bit. And in the end, that was the value for this example. Does this make sense? It's pretty much like kind of like a hardware binary search, just constantly comparing between your input voltage versus a dynamically changing reference voltage, and that voltage is changed by 50% of the time, and then gradually you guys converge into the same value after however many bits that's been converted. I hope that makes sense. Okay, cool. So yeah, to give you like how the signal would look like. For example, on the left we have the input here, and then this is the amount of time it takes for the sampling to charge up the initial sampling and hold circuit. And once it's been charged somewhere there, and then we're gonna have the conversion period started. It's started at 50%. If it's higher, it goes to the second bit, and then it turns out to be lower, so it goes to the third bit, and then just gradually, converged into like a value. So the input was 0.69, and then in the end we have 0.667, give or take. So reasonable amount of accuracy, and the time it takes is also quite reasonable, because just considering you have how many bits we have here. If we have like a 4-bit system, at most you compare for like 4 times, or like you have 10 bits, you compare 10 times. So it's like a much controlled in terms of amount of resolution you get. So any questions regarding how they actually work underneath in this type of ADC? Okay, perfect. So like a quick summary here, the speed is kind of in between, like a good balance between the previous two. It is definitely slower than the flash ADC, but it's also not like imagine if you have like a 10-bit, then the previous version will go through like 1,000 cycles to determine at the worst case, but in this case it will only be like 10 cycles for like a 10-bit. Resolution, it's medium to high resolution because amount of time it takes, it's reasonable, and you can just assign more bits to it. Essentially, you're trading off between like a amount of time that's added linearly, and then you have one more bit to that. So it's not too bad of the resolution. Usually used for like medium to high resolution applications. And complexity, it does require DSE, so that's some downside, and some of the control logic. But generally speaking, at least on the analog side, like the hardware side, is relatively easy. And the power consumption, it's again like kind of reasonable. It's not the best, it's not the worst. So this is essentially like a balance between speed, power efficiency, and accuracy, and which is why it make it like ideal for STM32 microcontrollers. So goals for this class, basically, we were not expecting you to have like very, very deep understanding of how the circuit works under each type of different ADC structures, but you should be able to have like a big picture of the different types of ADCs and the trade-off they're making between them. There's not essentially like one, golden boy for all of them. It's always have some trade-offs. Some of them are fast, the flash ADC, but at the cost of more cost because the amount of hardware needed for that increases exponentially compared to the amount of bits you need for the resolution. And we also have the accuracy and other considerations. So keep that in mind, and then you should have like a rough idea of which one to choose from at a given application. And in case you want to know more about ADC at implementation levels, always feel free to take more analog circuit design courses. And in our lectures, those diagrams are usually going to be like simplified versions, give you a high-level idea of how they work. But if you want to dig underneath how to build the best ADC, then feel free to take more courses around this. So with that, let's just do like a quick exercise. You can please do talk to your neighbors and discuss, and then we will try to fill out this diagram here. We can do that together later, but I do want you guys to talk to each other first. If you have to put like a high, medium, or low based on these three type of ADCs, based on resolution, speed, accuracy, etc., please try to fill them out. This was supposed to be like a worksheet problem, but I thought because the spring break is approaching, most of the classmates, some decent amount of the class should probably not going to make it to today's class, so we're going to just waive this. So I will ask you to grab a piece of paper or use your laptop or tablet to write down the answer, and then we can talk after probably 3 minutes or so. Yep, talk to your neighbor.
Everyone knows resisting. Everyone's the most accurate. Probably the least Wait, that's what slope is? Parasitic resistance, or they like actually I think when you implement Flash, it's competing with opposed to like physically. Because if you have a player, that is essentially a linguistic item. Just like these little players, like all that big and that is essentially a fence. So you can use the wires. That's essentially the history of the existence. Wires need different figures. You essentially have a metal slash chip and you have I know. If you can make it how long is it infinitely fast? I'm gonna lay this out over a weekend in 427. I hate you.
I'm doing the LLM to buy pointers and make custom program assembly for every user in the program so that I can build hardware to do this is the project that I chose this. Never played my instruments. I forgot to do ampersand. Like that. I think the class is easy as ever.
Same row who I saw in office hours were
Doing it's because no one's been the ampersand that I got right. My rapper
Okay, all right, let's look at this together. What's your thoughts on the resolution between these three? Any volunteers? Which one is the highest resolution between these three? The highest resolution slope. Any other guesses? And why do you think it's slope?
It's also the slowest. It has I'm sorry, I'm not.
Oh, okay. Anyone else also think it's slope, the highest resolution? And yeah.
It's just constantly comparing the voltage on clock.
Uh-huh.
So you can just if the clock frequency is fast enough, you can get really specific with it.
That is correct. And what's the lowest resolution in most of the time? What's the lowest resolution between these three? Any guesses? Yeah. A flash. And the reason for that is?
Because it has a set number based on how many resistors and comparators there are. And the example earlier could only tell 8.
Yeah, that is correct. And it takes a lot of exponential amount of components to do a higher resolution. So usually they're more on the lower resolution end, and the SAR is kind of good to high. So how about speed? Any thoughts on these three? What's the slowest one? Yeah.
the slow configurator,
And the reason for that is?
because you use time as your unit of measurement, so it's slow.
That is correct. And I guess the fastest one is flash. We all know that. And because it's so fast, we're going to add a very fast on top of that. So it's very fast, slow, and fast. How about accuracy? Any thoughts on the accuracy between these three? Anyone, which one could have the highest accuracy between these three? Any guesses? The slope, and why is that? Okay, so you can just take a long amount of time and then you measure it, and also if you consider we have the dual slope version, so that can be like a very high accuracy one. And yeah, so pretty much like this. The flash is also very accurate. The resolution might be a little bit limited, but within that resolution, it's very accurate. The star is kind of medium accuracy because it depends on how many bits you assign to it. You always have like an inherent error in between, and then it also uses ADC to generate whatever the reference you're comparing it to. So that added another variant to your reference. So, but it's still a very decent accuracy implemented, even with the SAR. How about the complexity? Which one is the most simple one, I guess? Any guesses? Any thoughts? Yes. And the reason for that is?
I mean, it's just the voltage dividers and then comparators following together.
That is correct, because although it uses a bunch of components hardware-wise, but it's essentially just putting them in parallel and then getting one go. So it's a very simple in terms of like the structure-wise. So which one do you think is more complicated, like the slope integrator or the SAR? Any thoughts on this? Okay, they're kind of comparable, but if we have to do like what comparison, like slope integrator is kind of like mild complexity. The star is higher complexity, considering the logic circuit and the additional ADC needed within that ADC channel. So, how about power? This should be hopefully a more intuitive one. How about the power consumption between these three? Any thoughts? So we know that the flash is probably going to be the highest power, right? Because a bunch of the stuff linked it there. How about the slope and the star, the SAR? Which one is low power? Which one is medium power? Okay, this might be a bit confusing one, but it turns out it's actually the slope integrator is the low power one because it's pretty much just doing like the counting of the timer and then do like a comparator, right? And one thing that like the microcontroller is really good at and they do it very efficiently is counting time. It's those things are a lot of times built at the hardware level, so it's actually quite efficient in terms of power. And in terms of cost, I think it's pretty related to the previous ones. Obviously, the flash is going to be the highest cost because the on-chip resistors. Yeah.
The slope integrator has to constantly charge and discharge the capacitor. Is that not expensive in terms of power?
Which one? Like the
slope integrator has to charge the slope hardware capacitor. Is that not power hungry?
That's a very good point. So it's actually a very small capacitor, and it's a very small capacitor because the clock is very fast. If you were doing like megahertz clock, if needed, then you only need, even if you do like 10-bit, it's like 1,000 clock cycle, which is still a very small amount of time. And on the SAR, because the ADCs, you can think of them as you still need that amount of power to be held at a constant level during the comparison, as opposed to the charging up. It's you charge it up and then you leave it there. It doesn't have to power anything, etc. So it's you charge once and then decharge, as opposed to on the SAR, you actually have to charge it up and hold it there during the entire comparison, etc. Any other questions on this diagram? Hopefully they matches what you, or mostly matches what you had in on your sheet or on your laptop. Okay, cool. Yeah, there are also other like common ADC architectures. For example, the Delta Sigma ADCs, the pipeline ADCs. We will not go into a lot of details of these, but just so that you're aware, there are also other ADC structures out there. In case someone asks you during like a job interview or anything, just remember some buzzword. Anyway, so what we have on our chip, right? We were using the STM L4R5, and then we have on our chip we have the 12-bit ADC, which is capable at sampling at 5.33 megasample per second. You can also do that in like a 6-bit resolution, which give you up to 8.8 megasample per second. And the ADC can be connected to like 16 external channels, so you can sample different signal, not at the same time, but you can continuously sample them just one at a time, but connected using the same ADC to sample them. We also have 5 internal channels to do like some internal measurement and stuff. For example, the DAC outputs tracking, as well as the temperature sensors monitoring inside of the chip to just have like a monitor of what's the current stats of the chip's power consumption, etc. If it's overclocked or something. And you can also go up to 16-bit with some like hardware oversampling. But this is roughly the specs you're going to get on the ADCs on the STM we're working with. And we have some analog watchdogs, 3 of them per ADC. Those are used for like power management applications with, so that they're able to trigger some interrupt, so that if you're doing something that's more power management sensitive, you want the chip to go to kind of like sleep or doesn't care, unless something happened, you can use those for your interrupts. And yeah, let me just go through these quickly. These pretty much this is a internal what it looks like inside. It's using a SAR registers for the sampling, and then just like a quick recap, this is how it essentially works. Every time once the input comes in, hold at voltage level, basically the register will do the binary search 1 bit at a time from the most significant bit, and then gradually converge onto the value of this current held voltage value. And in case you want to calculate the conversion time, you should always usually consider like the worst case. Basically, the time it would take is the combination of the sampling time plus the conversion time. The sampling time is, basically how long it takes for the sample and hold circuit to charge up, and then the conversion time depends on how many bits you have, and then each cycle you can think of them having one conversion, one compare, and then just depends on how many bits you have. That's the conversion time you have for the. In this case, for like a 12-bit ADC, if we say the sampling time is 4 cycles, the whole ADC conversion time is 4 plus 12, the 16 cycles. And then if it's a 6-bit ADC, then that's 4 times 6, then 10 cycles, which less than like 1 millisecond, which is pretty decent. And you also have the freedom of assigning where the data goes on the register. This is mainly for any of the bitwise operations you want to do. Just make sure if you want to interact with this, make sure you remember where they are, and then when you do like bitwise modifications, these are the functions there for you. And we have the regular and injected. The regular is basically the regular ADC sampling continuous. The injected is it have the built-in interrupts. So you can use that as a hardwired interrupts to your program. using that to trigger, to use that for like some more higher critical or higher priority events, and then use that to trigger